Guys, my name is Will Buchanan, and this is my lab 2 for Physics 1. So for the introduction, this lab covered the gravitational force, and we first looked at an object that was dropped from rest, and then looked at that object's position over time. And this object's motion is compared to two different computational models. One computational model contains just the force of gravity, whereas the other computational model looks at the gravity force and the drag force present. So you get some different results when you consider just one force versus all the forces present. So this is what was used to track the object I dropped, which in this case was a fortune teller. And we see that as it was dropped, its distance covered between each time interval increases. And that's because the object is accelerating downwards due to the gravity force present. And the position versus time of this falling object, we see that this is sort of a curved line here. And this curved line of the change in vertical distance over time indicates that the velocity is not constant, which tells us there's a net force present and that acceleration is taking place. And what's going on here is the net force. So the net force is the sum of all forces acting on an object. And in order to predict an object's position, you need the object's acceleration, which is found in the force. If you do not have all the forces accounted for, the final position prediction of where this object's going to end up will be off. And the forces present here are the gravity force, obviously, and that accelerates the object at negative 9.8 meters per second squared in the y direction. Then there's the drag force present, which for this lab, we use the formula that drag essentially equals velocity squared. So as velocity ramps up, the drag force does so even much more than the velocity. And the proportionality constant is just to adjust to make sure the drag worked with our object in the computational model. And the v hat is just the direction of the force. And it's important to note that this negative here means that whichever the direction the object is falling or moving in, that drag force will be in the opposite direction. So in this case, it will be in the opposite of the velocity since the object is falling downwards. Then the gravity only model, the parameters, we have the weight of the ball and position and velocity, all 0 initially, and the gravity force of 9.8 meters per second. Then on this line, we look at our adjustments made, and here we have the weight force, which was that gravity constant again, and that will be our only net force present because we are not yet accounting for drag with this model. So then we can take this new F net we found and add it to the ball's initial velocity to get a velocity over, and then we multiply that by time and we get the ball's velocity over a set period of time. And then once we plug in that velocity times time plus the ball's initial position, we can get the ball's position versus the ball's time and put that on a graph as well. So the position versus time of a falling object, when we look at just the fortune teller, it did not fall as quickly as the model without drag. And this discrepancy here tells us that there's something else constant. There's something we're not taking into account. And that would be the drag force. So here we add in drag force. It essentially, again, is that constant, but what we're mainly focused on is it's the magnitude of the ball's velocity squared. So that's going to give us another force acting in the opposite of that gravity force, which will explain why it doesn't drop as fast as just gravity present. And since that FD force drag is added into the net force here, everything already works down here, and then we'll include the drag force. And then looking here, we see just real quick that the first model where the ball just falls due to gravity, but once we add this arrow, that's taking into account that vertical drag force. So more results. Once we add in the drag, it actually gets very close to the actual fortune teller falling. And when we compare velocities, we notice that the velocity of the model with drag begins to flatten out, whereas the blue one maintains a constant velocity. And in the real model, or the experimental model, the fortune teller, the velocity flattens out here too. So what is going on there? And that is actually because of terminal velocity, as that drag force increases more and more, but that downwards gravity force stays constant. Those two forces begin to equal out, like we see in this photo. And once those forces are equal, then velocity will stop changing and the ball will fall at a constant speed. So the final question is, what if the ball or object we had was initially thrown downward? Would terminal velocity in this case be affected at all? And the answer is no. Initial velocity would not affect terminal velocity, because terminal velocity is just a matter of when that drag force and net force equal out, and initial velocity has nothing to do with these forces at all. So whether you threw it really hard or just dropped it, terminal velocity would not change because it's just a matter of the forces. That's all I have today. Thanks for watching.